Okay, so why don't you go ahead and start with this warm-up. So we'll take the function f of t to be just a line of slope 2 that goes through the origin to t. And then we're going to compute 6 definite integrals. So first of all, the integral from 1 up to 3 of f of t dt. And then 1 to 2, 1 to 1, 1 to 0, which is a little bit strange. You're starting at 1 and then integrating back to 0, but we can still evaluate that. 1 to negative 1, and 1 to negative 2. Again, going backwards for those last 3. And then what we're going to do is use those values that you found from the definite integrals to try to plot a function that we call g of x, where the input x is actually the top limit of integration on these same type of integrals that we've been doing. So the function will be, again, the input is x on the top limit of integration, and it's the integral from 1 up to x of f of t dt. So what we're going to get is points from all of these 6 calculations that we did earlier. So this first point would be like when you plug in 3 for x, and then the result that you get from the integral would be the y value. And for this would be 2 for x, 1 for x, 0 for x, negative 1 for x, and negative 2 for x. And then we're going to see what that shape of the graph looks like, and maybe what the function is, and then how that relates to the antiderivative that we've been studying so far. So you can go ahead and pause the video now to complete the warm-up, and then I'm going to go over it in a little bit. Once you play the video, then I'll go over it. So, okay, so we'll go over it. So in order to make these integrals a little bit faster, what we can do is just write what the definite integral is. Or, I'm sorry, the antiderivative is for little f. So let's call it capital F of t. And that's going to be what we get just using the power rule, where we increase the power on t by 1. There, it's just to the first power, so increase it by 1, that's 2. And divide by that power, so divide by 2. So we end up getting the 2's to cancel, and we just get t squared for the antiderivative. So then for that first calculation, we'll want to calculate this antiderivative, evaluated from 1 to 3. So plug in our top limit first. 3 squared is 9, and then minus our lower limit plugged in, 1 squared is 1, and we'll get 8 for that first value. For the second value, we'll get t squared evaluated from 1 to 2. So top limit first, 2 squared is 4, minus 1 squared again is 1, and we'll end up with 3. For the next one, we'll again do t squared, this time evaluated from 1 to 1. And this should be 0, since this would just be integrating from 1 to 1 would just be that little vertical line segment, so not have any area. But of course, if we evaluate it, we'll get 1 squared minus 1 squared, 1 minus 1, so 0. All right, and then our fourth one is the integral from 1 to 0, so we'll evaluate our antiderivative from 1 to 0. Plug in 0, we get 0, minus when we plug in 1, we get 1. So that'll be negative 1 for that fourth one. Okay, and our fifth one, t squared again, evaluated from 1 to negative 1. Plug in negative 1 first, we'll get positive 1, and then minus 1 squared is 1 again. So we're actually back to 0 for that one. And then finally, we'll do t squared evaluated from 1 to negative 2. Negative 2 squared is 4. Minus 1 puts us back at 3. Okay, so let's use these calculations that we got to try and plot this function g of x. Let's get some axes here. 1, 2, 3. 3, 1, 2, 3, 4, 5, 6, 7, 8. down there. Okay, so using these points, this first calculation that we had would be the value that we get out of this function when x is 3. And then the result of that integral was 8, so we have a point at 3, positive 8. So 1, 2, 3, 8 up here. For the second one, that would be when x is 2. We got 3 out, so we'd have a point at 2, 3. Next is when x is 1, and we got 0 out, so 1, 0. Then when x is negative 1, when x is 0 next, that's when we got negative 1, so I have a point at 0, negative 1. And then when x is negative 1, we got 0 out again, so negative 1, 0. And then that last one is negative 2, positive 3. You can probably see what type of shape is being created here. It looks kind of like a parabola. For the function g of x. And also, if you think about what we did for all of these calculations, we are always taking t squared, evaluating the x value, and then subtracting 1 always, because that one lower limit is always staying the same. And you can also see it from the graph. It looks like this is exactly x squared minus 1, or just a regular parabola shifted down 1 unit. But also, we can see by looking at g of x that we're actually getting an antiderivative for f of t just with x plugged in instead of t plugged in. So if we actually took the derivative of g prime of x, then we'd actually get 2x from this x squared term, and then the constant just becomes 0. And we have that g of x is an antiderivative of little f of x. And that should make sense, because we were taking the antiderivative, and then that lower limit was staying the same, so we're just getting this antiderivative evaluated at x, and then a constant for that second part, and we're just getting an antiderivative back for g of x. This function, g of x, is also called an area function, so the picture that goes with it, and f of t. It's pretty interesting. So if we just draw f of t here real quick. So we've got a t-axis now. And f of t is just a line of slope 2 going through the origin. So all of these integrals are starting at 1 and then going up to some other value, and that value that we're integrating up to is going to be called our x value. So if we draw a vertical line here at 1, and then we think about what happens as a limit of integration increases from t. So if we started integrating this way, and looking at the area under the curve, we'd be getting positive area as we increase our top limit of integration past 1. We'd be adding area into this area under the curve, and this integral, this g function, is increasing as we go away from 1. But then if we actually go to the left of 1, if we plug in 0 or -1 or -2 as we're going this way, going past -1, so moving to the left, sorry, we aren't getting to 0 yet. We're actually subtracting area as we go from the integral of 1 up to 1 to 1 up to 0. And we saw that because we went from 0 to negative 1. But then as soon as we get back past 0, now this is actually below the x-axis, but since we're going integrating from right to left, it's going to become a positive area. So we can kind of see the shape of that graph. As we go from 1, we're increasing. As we go to the left of 1, we decrease a little bit until we get to 0, and then we start increasing our area as we're adding more in. So, and you can see kind of right here, it would be even between negatives and positives and give us that 0 area that we saw at negative 1. So this is called an area function. When the function is described as the area under the curve. Okay. All right, so